All right, so first let's start with information theory. All right, so first, what is a piece of information? So, let's just think about it. A piece of information, it tells us something. So, I'll give you two examples of two, statements that are technically pieces of information. So, one statement could be that there will be 24 hours tomorrow. Okay? That is technically a piece of information. Yes, it's true, there will be 24 hours tomorrow. Okay, now suppose this, okay? Let's say another piece of information is, let's say we just flipped a coin, okay? And so we flipped a coin, and let's say it landed heads. Lands heads. Okay, so let's take a look at these two statements and what they tell us. What this tells us here is something that we already know, something that we already expect. So even though it is technically a piece of information, there's not really much value here because, well, we already expect it. Now, this piece of information over here, well, this one actually has some value to it because a coin has two possibilities, right? The two possibilities are heads, tails, right? So the fact that we know that lands heads essentially eliminates 50% of the uncertainty. So what do we see from this? We see that this piece of information, statement number 2, is more important or has what's called a surprise factor, a greater surprise factor than this first statement over here. So we would say this piece of information is of more importance or of more value than this piece of information. And that importance here, as I just mentioned, is called a surprise factor. So this has a higher surprise factor. So statement 2 greater than statement 1. So how would we go about quantifying what the surprise factor of something else? Well, we just saw that it really depends on the number of possibilities, or it actually more so depends on probability, right? So here, the probability was 1. This is already expected, we know this. This one, the probability is 1/2, right? So what relationship do we see here? We see that the probability, or as probability decreases, the surprise factor increases. So let's say as P decreases, the surprise factor increases. Now I'm going to denote surprise factor by I for information, because in reality, that surprise factor is just a way of quantifying the piece of information here. Okay, great. So we have established this relationship that as P probability decreases, the I information increases. Okay, great. Now, what else can we deduce about information probability and how it could relate? So imagine we have this scenario now. Imagine we just rolled 2 dice and each die both rolled the number 4. Okay, so the fact that I rolled a number 4, or the fact that 4 is the outcome, well, 4 has a 1/6 probability of happening, right? Because the 6 outcomes are, well, the 6 numbers on the die, or the six sides. And it's going to be the same probability here. Okay, well, let's think about the relationship we just thought about with as I increases, the probability decreases, or sorry, vice versa, as probability decreases, I increases. Okay, well, what we see over here is, well, imagine we have this scenario. How much more information would it be, or what is the surprise factor of this compared to a scenario where we just have 1 die, right? Imagine we just have 1 die. Well, in that scenario, and it rolled a number 4, there's a 1/6 chance. But the scenario over here, we have 2 die. right? Or 2 dice. There's a 1 in 36 chance that both of them roll 4, right? Simple. 1/6 times 1/6 is equal to 1 over 36. Okay, so what we have now established is that there's some sort of relationship between, well, these and the surprise factor of this scenario. So how can we go about quantifying this? Well, let's say I of information is a function of probability, right? As we just saw, information is a function of probability, right? And let's say the probability here, we can denote this as P, and the probability here, we can denote this as Q, right? So I of P and Q, right, is gonna be equal to I of P, the information of P, plus the information of Q, right? That's going to give us the total amount of information that we gathered, right? But we also know this relationship exists where they're both going to multiply and then give us a different probability. So there's only one sort of function here that fits this sort of situation or this sort of criteria, and that is the log function. And I'll show you this right here. So one of the properties of log functions is that log of, let's say, variable x times y is equal to log of x plus log of y. Now, this looks very familiar over here, right? So in this situation, right, where we have PQ, right, what we're really saying is the total probability here is 1 over 36. And the probability here is 1/6, and the probability here is 1/6. So we can really denote this here, right? And we can map this to this situation as I of 1 over 36 is equal to I of 1/6 plus I of 1/6, correct? So notice how similar these functions look. Well, actually, that's exactly the point. There's no other function other than a logarithm that satisfies this. So now we have two things, or two properties, that we understand about I and about P. First, that as P decreases, I increases. And second, that there's some sort of logarithmic relationship over here, as we just saw from this situation. So we can do log relationship. Okay, so let's actually try, well, based on what we know, to figure out how this works. So let me give you an example. Let's say we do think that, well, based on what we know, we can just assume, let's say I of P is equal to, I don't know, log P. Well, I mean, this makes sense, right? Based on what we know. So let's test it out, right? Let's say we have a situation or an event, right? Let's say the event is that, we are going to school, okay? And let's say when we go to school, I mean, we don't know what our first period is. Some days it's math, and sometimes it's science. In fact, let's say there's a 50% chance that it's math and a 50% chance that it's science. Okay, well, let's think of how we can get what the information of this kind of situation means. Let's say this is the natural chance, and let's say we have found out that the actual class that we have is math. Okay, well, there's a 1/2 chance of that happening. So let's say I of 1/2 is equal to log of 1/2. Okay, well, what we realize is that the log of 1/2 is a negative number. It's a negative number, right? I mean, because let's just use a normal log, for example, right? With a log base 10 that we naturally have. I mean, 10 to the power of a negative number is only going to get us 1/2. And we can say about any whole number like 2, 3, 4, 1, etc. Any whole number as the base for the logarithm is gonna give a negative number for any probability because probabilities are from range 0 to 1, right? So, how do we go about solving this? Well, it's actually pretty easy. Just add a negative sign. So now, negative times negative equals a positive, and now all of our information is going to be positive. And we're going to see how this relationship now works with computers. Okay, so really quickly, here's what we've learned so far. We have learned that we have established this little equation over here, that the information as it relates to probability or the surprise factor, right? Again, is it really just a surprise factor? Because the surprise factor is how we measure information, and P is equal to probability. We have established this relationship. Okay, great. Now, how does this relate to AI? Well, in AI, everything that we learn is a piece of information. Everything that the AI trains on is a piece of information, and it needs a way to quantify it. And that's how this works. But screw AI. We don't even care about that right now. This is actually how information is stored on computers in bits. Okay, so let's go back to this function. So think about probability for a minute. Okay, let's say we have a situation where the probability halves. Okay, a probability is always halving. Okay, this happens a lot, right? The probability halves when there is, more outcomes or more possibilities. The probability tends to halve. So how can we almost make that into a beautiful relationship mathematically? Well, we can put I of p is equal to negative log base 2 of p. Now, let's think about this here. Why would we put log base 2 of p? Well, let's say we have a situation where the total probability is 1, right? The total probability is 1. Well, then I of p, or I of, let's say, 1 over here, is going to be equal to, well, what's log base 2 of 1? It's going to be 0. So I of 1 is equal to 0. And that makes perfect sense because the probability of this happening was already 100%, meaning we gained no new information from that statement. So it all makes sense mathematically. So now let's think about how this would work if, let's say, we had a situation where, again, a classic heads or tails scenario where there's a 1/2 chance of each outcome. Then, guess what it'd be equal to? Well, what's log base 2 of 1/2? Okay, it's just negative 1, right? And then we just put a negative sign in front to make it 1, right? Okay, great. Now, let's look at this. Let's say now we cut that 1/2, and let's say we eliminate another outcome or another scenarios, and that leads us to a probability of 1/4 for a piece of information, okay? Or an outcome that happens. Well, now, guess what? Log base 2 of 1/4 is negative 2, but a negative sign in front becomes 2. So it's a beautiful relationship here where each time the probability halves, whenever we have log base 2, then the piece or the surprise factor of the information essentially doubles. Okay, great. Or sorry, not doubles. What happens is it increases by 1. My apologies there. So for example, 1/8 would be equal to 3, etc., right? You kind of see the pattern here. Each time the probability halves, the surprise factor will increase by 1, not double, by 1. Okay, great. So, in fact, we can write that down here. We can write it like this. I previous. Okay, great. So how does this relate to computers? Well, computers are all, running this exact function over here. That's why computers store everything in bits. Everything's in zeros and ones. Why is it just zeros and ones? Well, it's because everything's operated under log base 2, right? And so whenever a computer stores a piece of information, it is essentially assessing the probability of that outcome there, and then it's using binary 2 bits essentially, or sorry, not 2 bits, in bits, it's using binary, and it's using log base 2 over here. That's how binary works, and that's how information is stored on a computer. And we're gonna see how that relates to machine learning, well, later, because obviously machine learning and AI is all built on information.